In this video, our goal is to consider two major rules that are used for approximating areas under the distributions that can be used to model random phenomena. So we first of all look at Chebyshev's rule. Chebyshev's rule applies to any distribution. In other words, it could be a right-skewed distribution, a symmetric distribution, or even a left-skewed distribution. It could also apply to the unconventional distributions, as we might see in this case. And it pretty much has approximate rules that we tend to use when we have no access to technology of any kind for calculating areas under or the proportion of certain populations that meet certain criteria or that are within certain bounds away from the mean. Here's what I mean. For instance, if you collected data on, let's say, 1 million adult males, and it is pertaining to their heights, and someone asks you, well, even though you don't know what the mean is or what the standard deviation is for all of these heights, can you give an approximation of what percentage of these heights are within two standard deviations of the mean? Well, using the Chebyshev's rule, you can say at least 75% of the data on heights will be within two standard deviations of the mean. A typical question we get when we teach this is, where did they get the number 75%? Please note that the Chebyshev's rule provides a lower bound, with emphasis on the word at least, which means at least 75% of the data will be between two standard deviations of the mean, means that it could be more than 75%. If we say at least 89% of the data is within three standard deviations of the mean, it means it could be more than 89%. These are mere approximation rules, but that is not to undermine their importance. A stronger rule is the empirical rule. It is stronger in the sense that it is more restrictive because it only applies to bell-shaped and symmetric distributions, and it tends to be a little bit more exact because of its restrictive nature. And it does say that if you locate the mean of a bell-shaped and symmetric distribution, which a normal distribution is one of such, if you take one step, and by one step we say one standard deviation from the mean, so I'm going to call that one standard deviation will be represented by this population standard deviation from the mean. I'll arrive at a point, then go back to the mean. If I take one standard deviation back, I'll arrive at what? Mean minus one standard deviation. These are the points of inflection that we outlined earlier. The proportion of data collected on the random variable x of interest would be between these two values, the mean minus one standard deviation, and then the mean plus one standard deviation is approximately 68%. There's an emphasis on the approximation here. So it is never exact. Sometimes you might get exact, but it is not always exact. That is what I mean to say. Then also, if you took two standard deviations back, 1, 2, from the mean. So from the mean, take two steps back, or two standard deviations back, and then go back to the mean, take two standard deviations forward. So from the mean, two standard deviations forward, you will get approximately 95% of all data captured within that range. Similarly, for three standard deviations from the mean, above and below, for that stretch, you'll be capturing approximately all data points, but not all. So you are capturing approximately 99.7% of all data values. To throw a little bit more light on this, I have an example here. From 1984 to 1985, the mean height of a 15 to 18-year-old male from Chile was 172.36 centimeters, and the standard deviation was 6.34 centimeters. Let y be the height of a 15 to 18-year-old male from 1984 to 1985 from Chile. So that is the variable of interest that we're observing for that population, y. And we have been told that y follows a normal distribution. So this is shorthand for y, the height, follows a normal distribution. And the values in the parentheses, we've seen them before. This is the mean. It is always the first value, which is written in shorthand as mu, equals 172.36, and the standard deviation is the second value, which is 6.34. Since y follows a normal distribution, the mean value is always placed at the center, which is 172.36. Then, from the center, we can take a step or a standard deviation forward. The size of that step is 6.34, so that if we added what? These two values, if we said from 172.36, if we added 6.34, we would arrive at the number 178.7. If we took another 6.34 sized step forward, then again we would have 185.09. If we took another side 6.34 forward, we'll arrive at 191.38 centimeters. Let's go back to the center, the mean. Take 6.34 steps backward. What do we have? We have 166.02. Then from 166.02, take another step, 6.34 backward. We arrive at 159.68. Then take another step, 6.34 backward. You arrive at 153.34. Okay, with this, we have been told that y follows a normal distribution, which means it is bell-shaped and symmetric. And if our goal is to find some approximations of areas under this curve, for instance, we are asked that about 68% of heights lie between what two values? Without a calculator or without an exact computing machine, we can use the empirical rule since it applies specifically to bell-shaped and symmetric distributions, of which a normal distribution is an example. So applying what we learned here under the normal distribution, I can say that it follows that about 34 about 34% here, 34% here, that will be a total of 68% lying within one standard deviation of the mean. Then, according to what we learned, 95% lies within two standard deviations of the mean. And lastly, approximately 99.7% lies within three standard deviations of the mean. Okay. All right. So approximately 68% of the heights lie between what two values? That would be between one standard deviation of the center value, the mean value. And so that would be between 166.02 centimeters and 178.7 centimeters. Okay. And it follows then that the next question, what percentage of the heights are greater than 159.68 centimeters? Well, we can tell from what we have done so far that if 68% is concentrated within one standard deviation above and below, 95% between two standard deviations above and below the mean. So that means 95% minus 68% right here would have a total of, so 95% minus 68, that would be a total of 27%. And divided by 2, we have 13.5% and 13.5% here. Then further, within three standard deviations of the mean, you have 99.7 minus 95%, that will be 4.7%. So split that 4.7% into 2, you have 2.35% and 2.35% here. All right, and for the tiny tails here, that will be 100% minus 99.7%. So we're left with 0.3%. So you have 0.15% here and 0.15% here. That sets us up for finding what percentage of the heights are greater than 159.68. From 159.68 all the way forward, we have 13.5%, 68%. So let me write that down. Plus 68% plus another what? 13.15% plus 2.35% and plus 0.15%. Well, that would be the same as saying the total 100% minus the area to the left of 159. So that would be minus 2.35% and minus 0.15%. 0.15% and 2.35%, and that would give us 97.5% or 0.975. Again, for question C, what percent of heights are greater than 191.38? So this is where 191.38 is, and the only percentage above it is 0.15 what percent based on the approximations. Then finally, what percentage of heights are between 159.68 centimeters and 178.7 centimeters? So between 159 and 178. Let's look at the picture. So that would be 13.5% and then what, 68%. So we have 13.5% plus 34% plus another 34%, that would be 81.5%. Let's write this right. And so this is same as 0.815. Okay. In the next video, we're going to move away from approximations into finding exact sizes of areas on the probability distribution curves.